All right. Team. Okay, cool. Networks are cool. Cool. And they're everywhere, right? There's the social network thing, which everyone is excited about, but has existed forever, but we sort of put it online so we could harvest the money out of people and stuff, So they're everywhere. You're full of them. You're sitting here full of networks, right? Your brain, all the stuff distributing the foods that you ate and will probably put you to sleep in the next hour, right? I mean, they're everywhere. Okay, so we kind of always knew that, and that's what this little bit. So I have just to finish a little bit of where we were with this introduction from Tuesday. I'm going to talk about some example networks. We have videos, which may or may not run. We'll see how they work. But fun videos. Visualization of networks is hard, and I'll talk about that a little bit. Okay, so it's connected. All right, thing. Let's see if this thing behaves. Okay, so networks aren't new, right? They're not new. They've been around forever. We've thought about them for a long time in different ways. We talked about the origin of the word. People like to talk about Euler. Euler thinking about the bridges of Königsberg and thinking about a trip. It's a very geeky math thing to do. Just like, is there a way to get around all those bridges without crossing again, and so on. That was a nice little puzzle that Euler was fond of making up and for himself, and then solving rather immediately. There's stories of him, like some monk who'd spent 40 years trying to get one more digit of pi, and Euler comes along with some crazy series expansion involving sines and causes and gets another 20. Which is, disappointing, right? So anyway, so there are these mathematical kind of stuff where people have started to think about networks. Da Vinci, I probably said this, thought about blood networks and river networks being similar and trying to draw those analogies. Okay, we've had graph theory, right? So this is we trace it back to Euler perhaps as the first sort of mathematical version of thinking about what we call networks now, but it's a bit funny. Networks and graphs, surely they're the same thing, but they're not quite the way we frame them. Complex networks sort of applies to a different set of stuff now. So we have a social network theory. There's literature for that going back into the 30s. Again, it's this asking people who they're connected to and so on. And really, a number of you have seen these words before. Lots of data. That's really the transition, right? So late 90s, that we worked out that internet thing, right? We had DARPA and ARPANET, 4 computers connected in 1969. That was a little seed, and it took off. Got to the internet, then we put this web thing on top of it, and then we started to share data in a really easy way. When I was going through my PhD, I was still at the stage where you could get a postcard from someone that said, "Please send me a copy of your paper." Right? You'd have a set of these sorts of postcards, right? And you're just like, "I want this," and send it off. And this is the system, right? So it really was literally sort of a system of tubes and pipes, and you'd send physical objects through them, right? All right. Anyway, terrible. That's why I try to give you PDFs. Okay, so, all right, so this is fantastic, but it's also a disaster if you have beautiful theories because they're usually wrong, right? When you look at real data. So that's been it's a great time. The problem is the data is so much that we kind of think that's everything, right? So say all this social data we have now, Twitter and so on, very exciting, right? And there's so much to contend with. You think like, even just managing to understand anything in that seems like a complete victory, right? And you've understood humanity, right? And you've got the whole Asimov story, how to predict the behavior of people, all sorted out. But that Twitter itself is just some trace of all of human behavior. And okay, so more data will come, bigger and bigger and bigger problems for us, but it's great. We're doing the right thing. This is really science. So it turns out one of the big observations, and I've said this in Parks, we'll say it again, is that real networks are they're in a sense very rare if you just think of all networks in a box, right? So you take all networks of size n with m edges, just shuffle them all around and then pick one out. It'll never, I mentioned this the other day, there'll never be a good example of a real one. So they're very low entropy structures. That's sort of the big first observation, right? So we were looking in the wrong spot. Yeah? Okay. Classic human behavior, yeah. Okay, so, and something that does separate, I will say, from graph theory, which is a beautiful field, and lots of good things, lots of counting, mad counting of stuff, count, like how many triangles, how many little shapes are there in my graph, lots of things. I mean, it's a very rich field, lots of beautiful mathematics. Is that the physics approach is that, and science in general, is to try and elucidate mechanistic explanations. I mean, it's a very simple thing, but you need to both describe these networks so we get a handle on them, and then we want to start understanding how they come into being, how they behave. All right, so as I said, scale-free networks is sort of the big first story there. It's a rich gets richer phenomenon, but there are lots of other networks to think about. So string theory is the one that, if you really don't like measuring reality, then, and you do like math, that is the place to go. You are safe. Yeah, you can spend 10 years proving that no one will ever measure anything that could, mess up your theory. Okay, so very good. Well done, physics. All right, so and I've said we can get a little too excited about it. So there was a paper that was article in Wired a few years ago, the end of theory. No more theory. We don't need theory. We've got tons of data. Machine learning, we'll just make a big matrix of which things point to which things, which is fine if you're Walmart or Amazon. That's cool, right? I mean, that's okay. We don't care why people buy the 3 wolves baying at the moon t-shirt and the gallon of milk stuff. I don't know if you've seen these things. They're very fun. Part of the collection of great reviews on Amazon. You should, if you have not seen them, you should see them. There's the Badonkadonk tank as well, which you can buy. I think it's like $100,000 for your own military tank. For whatever reason, people who looked at this item also looked at this item, right? So generally speaking, that works quite well, but people are funny things. Anyway, so Amazon doesn't really care, right? They don't really care. They have an algorithm that pretty simple. It says if you bought this thing and then you bought this thing, you bought this thing, we'll just put those beans into some big bean counting matrix, and we'll start to front those what's that? And they count beans, and some machines count beans, and they make lots of machines, and you don't look at it after a while, but it works, and that's pretty good, and you tune it and so on. Okay, so we got a little excited here. So no more theory. This is really not right? So we want to describe things absolutely, and that's the bean counting stuff, really good. But then we want to understand why it comes into being. If we're scientists, if we want to make tons of money, maybe not. Okay, and that's really these characters here. There's unreasonable effectiveness of data. There's some people at Google, as I recall. This little line, unreasonable effectiveness of X, has been around since this paper by Vigno, which was a philosophical kind of piece. Why does math describe anything kind of thing, right? All right, we're not going to go into that, but it's a good question, which you can get upset about, and then you can stop thinking about it and go back to having math successfully do things for you. Counting's a big deal, right? Okay, so as I said, description, big deal, and the great thing now is we can describe a lot more, right? That is really, really exciting, right? We're not just saying, oh, I think people do this. Well, you can actually go and look. So fields are changing. So economics is very, very slowly changing itself to recognize reality. Lots of other fields are doing that, and other fields are just simply being political science. Tons of data. Who voted in which way. You can't. You need to still do these things where you go and ask people what they do and so on. That's fine. You need to do that, but there's all this extra material that we can get at. All right, fine. Okay. So I'm going to give you some nothing out of control here. Just some simple, just the base definitions we'll use over and over. In math, we tend to use vertices and edges, and we write G for a graph and stuff like that. The physicists are messy people, and they get things done, and a mathematician 40 years later will prove it as being okay, right? So that's sort of how it works, yeah. And the physicists are like, thank you. They do horrible things. All right, so we'll say nodes. Nodes is a little more plain spoken. But that could be anything, of course, people, forks in rivers, right? So where two streams have a junction, or in blood networks, how proteins interact. I'm going to give you some sort of very overall raw taxonomy, I suppose, of networks that I've had sitting around for a while. Web pages, how they interact, if you think of the big graph of the web. Organisms, food webs, who eats whom, right? Yeah. So that's a great data problem, right? How do you remote sense? I mean, we're basically talking about remote sensing is the big deal. How do you remote sense who eats whom in an ecosystem? And we have some crazy things where we put some little traces in, and we can see that this guy went through a piranha, and the piranha went through a such and such, and yeah. little bit. But it's hard to get that, that really big amount of data. Like we can do it now with satellites. We can take pictures of landscapes and get out things like where all the trees are. And of course the NSA is doing all sorts of hard, solid work to find out what all the people are doing, right? And we can, because we're like, hi, tweet, So animals don't tweet. I just ate an excellent skunk. Obviously we should add that to them. Yeah, all right. Okay, so nodes and links, all right? Barabazi's book is Link, so there you go. They're going to be the connections. They can be certainly real fixed, wires, actual real links. They might be dynamic ones, and so I'll show you some nice videos of airline routes, right? This is really, we've developed the whole airline system, and of course you can now simply just look at it. There are the continents and the way they're laid out and where cities are, and there's a history of development. It's just, that's the platform, right? You can make up a little grid and have people kind of interacting on that, and that's fun, but this is the world, right? This is how things might spread on our planet. All right. They can be abstract ones with physical impact, is what I'm going to say. So Google, for example, starts, it works when it appears in 97 or 98, and you're like, oh my God, this is fantastic, So it gets more traffic, and then they have to pay people to, just deploy machines, right? People who unpack boxes and put machines, right? Really, and of course it's gone on and on and on, and now with these enormous server farms, possibly destroying the Earth. Okay, so they can have that kind of impact, right? So they're abstract in a sense, but you add links and that matters later on. There's a cost, right? Either the website explodes or people start to pay more money somewhere. But they could be abstract in a pure way, so connections, I don't think they necessarily have a monetary, physical kind of impact later on, but so concepts, for example, semantic connections, thesauruses, right? Those sorts of things. All right, so I'll have some examples of these. Certainly, they can be certainly directed or undirected, and an amazing amount of work had to go into figuring out just undirected networks. And then, of course, they can be binary. They can be weighted, right? You very naturally have weighted networks, like how strong your friendship is, or what color that friendship is, and so on. Money moving between organizations and countries. Yes.
Can you use the word links is used instead of edges?
I guess it's just that, the physicists got excited and they started to use their words. And they wanted, the mathematicians are a little more, elite and stuffy or something, and we're not going to use those. I mean, edge is a good word, but I don't know. I mean, edge can be also, it's a bit ambiguous, right? It's the edge of something. That's a bit funny as well. A link really connotes more of that, what it is, I think. I don't know. Vertices is a little too much. It's a bit pretentious. All right, they can be binary weighted. Turns out this is very hard. This took many years for us to start to, come up with measures and so on that would tackle these guys. And indeed, what happened mostly for a long time is people would take dynamic networks, collapse them, and pretend that all of these interactions had kind of happened at the same time, and make them all undirected and make them all binary, ones or on or off. And they were fun networks to look at, right? So, but of course they're temporal. So we'll get to that. So it turns out a big piece that was sitting around forever, and people quantified this thing, wrote it down for pure random networks and thought about it, but it really is sort of the elephant in the room is the so-called degree distribution, and the first part of that is just node degree. So we'll use the word node degree. So it's the number of links that a node has around it. Now that's then complicated by whether they have weights and so on, and whether they're directed and undirected. So a nice first step is to say how many directed edges are coming out, how many indirected ones are coming out, and how many undirected ones. That might, you have to think about what your network is, but that's very normal. But then weights as well, hard. What do you call a degree when it's weighted? You kind of have to add up the weights maybe, but you also want to know how many things they're interacting with. So some of the methods we use for just undirected binary networks fall away a little. Okay, so if it's just the number of friends you have, regardless of their strength, then it can be, you can have 0 friends, which is a bit sad, 1, 2, and so on. And then we talk about the average degree of a network. So these are just really big pieces, right? The average degree, and then really the distribution of the degrees of a network govern a lot about whether things spread. The chance that it will be have a giant component, for example, and, right, which is that there's a big clump of them that are all connected together in some way. We'll get to that. You'll see in the literature, because physicists like to, that's kind of cool to have these things, so they put this. I like this. Sometimes, for some reason, the average degree will be z, but typically k is the notation used. K sub I. I is a node, right? So when you're reading through papers, this is generally what you see. And of course, there are an unreal number of papers to read through now, so don't try it. Okay, so very simple relationship. So if we have m edges, or m links, then each link is connected to a node on both ends. So that's, if you think about the degrees of those nodes, you're getting a +1 here and a +1 here. So you get 2 times the number of links, give you the number of little bits of degrees there. So if we multiply these pieces together divided by the number of nodes, then we get the average degree. Okay, so this is a simple connection. Right. Yes.
For counting links.
I said edges. Yeah.
For counting links for directed graphs, you thought maybe it's just the total number.
Yeah. Well, then you have the average in degree and the average out degree is what you talk about there. That's right.
And then
So then it will be just the number of, because there's only one end, it'll be the number of directed, yeah.
And then for undirected though, like how do you go about counting links in an undirected?
Oh. Well, it depends how you store your data, but I mean, it's basically, yeah, you just. Okay. Well, okay, I'll show you a thing in a second. All right, okay. All right, let's do that. Right, so directed networks, they have to be the same, they have to match up. Okay, m divided by n. All right, and I do different things here, but we will talk about, that's another useful piece. Maybe I'll make that color graphic. The neighborhood of a node, right? So in a lot of networks, if you get out to 3 steps away from a node, so you have a node that has its friends, and then the friends of friends, so that's 2 steps away. Friends of friends of friends is 3. That's really kind of the edge of the influence that you can have in social networks, and we talked about this in POX. That's sort of the horizon of your universe in a network. And once you get out, if you have someone who's 4 or 5 or 6 steps away from you, they're pretty random, right? There are a lot of people out there, and they're pretty random, right? If you compare them to a randomly chosen person, they won't be so far away from them. But your friends are different to random people. Typically. Okay. For special people. Okay, so we have an adjacency matrix, which is a very easy way to store things. Huge matrices are usually sparse. Huge networks are really, complex networks are usually sparse, so there's usually a ton of zeros in here, and you use nice methods to store sparse matrices. You can also just record the links. That's also just a nice thing to do, right? Just don't. But there are some linear algebra things that you might want to do now and then, which are totally fun, and it's linear algebra, matrixology, which is cool. So it's nice to have it in this way. So this is very simple. It just says, so node 1 is connected to 2, 3, and 4, right? So it's indexed across here, 1, 2, 3, 4, 5. Let's say 1, 2, 3, 4, 5, or it could be A, B, C, D, E labels, whatever the labels are. So this says that the second node is connected to the third one and the fifth one, and these are directed edges. So depending on how you want to play around with the data, you might have, let's say we just have a little network, and node, let's make it, this is a trivial little network. It's just this, right? Right? A, B, and C. So this will be directed if it's like this, and we might, depending on how we play around with things, if you do this, then that's you kind of have to just say it's a directed network, and this just might be useful for calculations to have it symmetric, right? So counting the number of edges then is just what's in the upper triangle, but you have to say how you've defined, right? This, in a sense, kind of you could think of as having, right? Because you've symmetrized the thing, it means that their edges are going both ways. So if it's a huge thing with just a few ones, but it's symmetric, you could think of it as being kind of like this. But you just count the ones above the diagonal. Okay. Yeah. Or you simply count all the ones and divide by 2. Yeah. Right. each one here represents an in part of a, yeah. So the switch between, you have to be careful with this, and in fact we move away from matrices for random networks. We did do this, it was kind of cumbersome, we have some papers on this, but we moved more to a probabilistic description. So if you're a node of degree 7, here's the probability that you are connected to nodes of degree 8 on an out edge and an in edge from one called Barney, right? You have all these different kind of, you write down a probability function. So you step away kind of from this picture. Okay, sparse matrices. All right, so, okay, complex, what are these things? So they're usually, right, they're large, they're sparse, which means not many edges relatively. There are some things with a lot of edges, but generally speaking, that's true. There's usually a dynamic element and some evolution, so that's very complicating. As I said, analytically, we are still really getting to those things. And, they can be all sorts of things, right? Networks are all over the place. We are in them, we are part of them. Yeah, good. All right, so, yeah, it's a great framing, good words everywhere. It's not like we've made up some funny little thing and, now we're just playing games with them. This is super real. All right, good. Okay, so this little taxonomy that I have, let's move through this, and I have a few little videos I try to insert. We'll see how they fare. River networks, neural networks. So these are physical ones, right? There are real links. You can go and look at them and poke them and do things to them, right? And measure them and so on. Blood networks, the internet, not the web, but the internet. There's a example of how these things are hard to render, especially if you project it onto a screen like this. So lots of beautiful things in river networks. I did my PhD on this stuff, and we're going to talk about branching networks more generally. So there's a very evident, beautiful fractal structure here. Leaves are more complicated in that there's a lot of looping and so on, and it gives them an extra kind of layer of resilience. You can, cut out the middle part here, and the thing will still function, right? The aorta, if you like. So they have lots of interesting pieces, and people are still absolutely working on this. There are papers coming out all the time about leaf patterns, so that's a lot of good fun. Road networks, very interesting. You can look at what's actually been laid out, if it was planned or not. You have maybe Europe is a good example where things weren't always, they evolved, they weren't always planned, right? And then you look at, say, the west of the US and just gigantic grid structures, and it's like, okay, that's not very natural looking, but, old parts of cities versus new parts of cities. Lower Manhattan, who knows where anything is, and, up above Houston, you're like, okay. Okay, power grids. One of the great examples that we have to contend with now of complex systems. We have a nice enterprise here at UVM on the smart grid stuff, because we need to build an immune system, right? We've made a nice big network, and that was good because it's nice to have lights, and we didn't have them for a while today, but that was, upsetting. So we figured out we need to kind of build some clever thing on top of it, which can respond, and right. That system, what happened was you had nicely designed local ones, right? And then they're connected for various reasons, business and all sorts of things, and some money and so on. So different things. It's not designed from the ground up. If you built one for the US from the beginning, it would be different. And it gives rise to some surprising outcomes, right? The motives for the individual stations are to just get off, right? So if things are bad, they just pull themselves off. So they're selfish. They're behaving selfishly, but that can have cascading effects. If everyone starts pulling off, someone's like, boom, they're not watching essentially. So you need more coordination. So that's more of an immune system type. The analogy of immune system is quite reasonable. Okay, and so for physical ones, we have distribution ones and redistribution ones, and I mentioned these the other day. Two broad categories. All right. Okay, this may work. Oh, good. Even has music. How about that? Yay. The music is really unnecessary. So you can, this is part of a longer bit of footage, but it's just simply looking at plane flights, right? So you can see the US lighting up as the day goes through. This is from a few years ago. And, if you put back, yeah, right. Which I'm going to, awesomely, yes. Oh, maybe the Caribbean a little bit. Right. Okay, let's, yeah, this is another one. So this is about 2,500 flights, is it? Something like that. This is from Brockman. I'll show some more stuff. This is not in time properly. It's just like, boom, these are where they all go. But it gives you, it's a pretty messy looking network. Bit of a hairball. So I'll show you a couple of things attached to this about how, we just talked about this in the reading group yesterday, paper that came out in Science. A couple of people called Dirk, they're both called Dirk, about, very simple way of thinking about this actually. So you can figure out, based on where diseases appear, just from the plane system, you can figure, that's the claim, and it's a pretty good paper, of where it started, based on the shortest paths from, was it Mexico City, was it, somewhere in Australia, right? You can see. So, all right, I'll show you some both some video and some pictures that we'll get at that in a bit. So I'll stop blathering about that. The blogosphere, which still exists, I suppose, these are now interaction networks. This is a bit of a different thing, right? So they're not physically laid down. There's interactions that may go up and down. The flight network is a good one, right? There's not actually a big tube where people are kind of running around. It can change and it's flexible. It has very different properties. The flight network, by the way, is an interesting attempt to create an all-to-all network, right? So ideally, you'd be able to get in a plane and fly to wherever you wanted, one big flight, right? That'd be great. But the hub structure allows that to be a pretty good approximation with many, many fewer flights, right? So if you want to have every place connected, and there are n places, that's n choose 2 flights, right? So it's n squared, it's n times n minus 1 divided by 2, it's n squared over 2. It's very big, it's a large number. So we'd have a flight from Burlington, Hawaii, or whatever, right? It'd be really silly. But the hub thing takes out almost all of those connections, and you can get to most places within 3 hops, which is pretty cool. Okay. So there's a necessity aspect there, right? Money that force that, and evolution is up against these sort of things too. It's costly to have all sorts of connections. In some cases, it's encumbering, right? You don't want everyone talking to everyone at the same time. That doesn't work, right? And we know that's, the military, for example, has tried to figure this out. The army started to get all these chest-top computers and things, and then what are we going to do, right? Like, do we let everyone talk to everyone at the same time, or how do we structure it so this thing can function? We have everyone turned off. I mean, okay. Okay. So lots of things. There's the gene-protein networks, which we continue to get better and better data about those things. Who eats whom? Airline networks, we've had this. AT&T has had their call network. Has been a thing that people have studied for a long time. There have been mathematicians at AT&T and physicists and so on working for many, many years. The media is an interesting interaction network. Very complicated thing, right? Now, of course, Twitter and so on. I mean, you have all this stuff, people following each other and repeating each other. Okay, so this is a little kind of interaction network. It's a physical one. This is a bit of a it's a TED talk. Come on, thing. Do you think it has to load all the way up and then start?
No,
That would be silly, right?
no, they limit you 30 seconds to save bandwidth for themselves. So they only queue up 30 seconds of buffer time.
But is it trying to search for it? Because I just want this little bit. So I don't know if so Montreal has this, New York's just started this, lots of places have these things where you pay a little bit of money, or you have an account and you take your bike and there's a bike rack and you take the bike and you ride off to another place and leave it in another bike rack. So yeah, right. And they've started them years ago and they all got stolen, like that, right? I mean, I think 15 years ago there have been various attempts to do this and they all get destroyed and stolen. Humans, I guess, have evolved enough to be trusted. Okay.
At the moment,
Can you hear that? Oh, I'm so sorry. Okay, you be quiet. So, it's a TED Talk. You can look at the rest of it. Yeah, so Hyde Park is here, so people are, having a nice time. These are tourists mostly. Had the fortune to ride around there in the rain vigorously recently. Cold rain, which is good, London sort of thing. Trying to go as fast as I could, but it's a so they put little traces on, right, just to allow it to start to see some structure, and so you can see what he was trying to say is you can see people commuting and so on. So these are nice visualizations. It's in 2 dimensions. It's not out of control, right? I mean, if you try to do this with gene protein interactions, it'll be just horrible. But anyway, so that's fun. You can look at that. This is I'm throwing in a few little examples as we go along. This is a paper that I've talked about with some of you before. This is from Science a few years ago. Cesar Hidalgo, who's now at the Media Lab at MIT. Very nice thing. They just looked at, in a sense, the vector of products that countries produce, and then try to match them up against each other and look at them, how they've evolved over time, right? So so there's this kind of resulting, this is a messy thing they're trying to reveal. There's all sorts of somewhat naughty little things they've done to kind of get it into 2 dimensions. But, the idea is that these kinds of industries are adjacent to each other. So typically if you're tropical agriculture, you have bananas and pineapples and so on. Fishing is probably something else that you might produce. That's the idea, this adjacency here. But it's further away from mining, right, for example, which is over here. And, and electronics is down in this section, vehicles are here. There's a big core in the middle. And so you have, if you look around the world, you have countries that are on the periphery here. They haven't moved into the middle. So there's and the claim is that there you can see the evolution of cultures, right? And you don't see places jumping, right? They don't suddenly produce, I mean, a little bit, but not, they don't suddenly jump right into the middle of it. Anyway, so a nice, it's a very nice piece of work, this one. All right, so that's a great kind of interaction network. This one you guys have seen. So this is, snogging means kissing, okay. So this is, if you can see this is a picture. It's pink and blue, so it's for girls and boys. It's from a high school in the Midwest, I think unnamed. So Peter Behrman is at Columbia. Well, I was there for a few years. A great guy, does all sorts of interesting things. Did a really nice piece on doorman, and he has a book called Doorman in New York City, because the doorman, getting a job as a doorman, there's no advertising ever. People just become doorman, and it's this really interesting referral process, and it's really kind of cool. So he's done lots of things, but actually vows of chastity, that stuff, right? Texas kind of thing. Whether they do or don't work, tend to find they didn't work. There was a delay, but it was more dangerous, and so on. So I mean, he's a sociologist, and he's done a lot of interesting things. Anyway, so this is a cumulative network. So the problem with this is you look at it and you think, wow, you put a disease in here and it's going to spread, right? But this is over some period of time, 6 months or a year. So there's some sequential history to this thing, and we want one of our visualizations of how things were carried out. So there are actually numbers under here. You can't see this. So here's here's what traditionally the world wants. I suppose that this is sort of not all cultures, but this is just a one pair that's stable, I suppose. Anyway, there are a whole bunch of those. There's a larger number here. You can't see it. Anyway, interesting piece of work from a few years ago. So these are interaction networks. Now we're just at social networks. Lots of different things. Boards and directors are an interesting bipartite. This is a great example of a bipartite affiliation network. So you're on a board, and maybe you're on another board over here, and then that starts to connect you with other people, and then those people are on other boards. So McDonald's, you go from McDonald's to such and such to such and such to the president's cabinet or something like that. I mean, there's some kind of interesting structure there. So we'll talk about those later on. These are really interesting. There's nice math involved, but they're really fundamental kinds of structures. These affiliation networks, I'll mention some more examples, but we'll really get into them a little. There's some work I'm going to add to this, actually. Well, there's some there are people, say, and then some venues up here, some way that they interact, and from that you get a network, right? So you don't want to throw away all the structure. From that you get a social network. It's much the better way to think about how people interact, right? They're in context, right? You're in a classroom here, maybe you have a religion, you go to a church or whatever it is, you go to some venue like that. Sports, maybe you play Halo with a bunch of people. The people are brought together in these different contexts. And they're usually somewhat small groups. All right. Actually, when I've edited these slides for years, right? So I used to have MySpace here was MySpace and Facebook. And this is funny because I have had this for a while. I mean, we're remotely sensing this data, right? And so it always felt a little bit bad. Email's very tricky because you can't get that data usually. We did have a big data set at Columbia, but it was all anonymized, right? So it was scrambled and all of the content was gone. The Enron data set is out there. You can get that one because Enron was very bad. So all of their email is just in a nice big package and people can go and analyze that. All the things they said, yeah. So if you do things bad collectively as an organization, then all your stuff gets out there. But that's been harder. So Facebook, of course, is closed. That's harder. Facebook has its own data team that does a lot of stuff. If you become friends with them, you can go and visit and come away with a graph. You're not allowed to bring data away. You're allowed to take your graph away. Just the way they started. I mean, Facebook's big draw was that it was closed, that it was clubby, that it was Harvard, and then it was colleges, and then, my God, high school people and parents. It's disgusting. Right, all along, that kind of has been painful. Yeah. They wanted to be Twitter as well. They realized that Twitter was this. They wanted an aspect of it. Yeah.
My advisor, my alma mater, went to Facebook on a sabbatical from the university.
Oh yeah, right.
I was working at Facebook now for like 6-8 months, and just temporarily.
Yes,
And so
which you can. Yeah.
Young professors into their club.
Yep, that's right. Lada Adamic, I mentioned, she's been there. And certainly there are people in academia who end up in these places. They stay there. Yeah. Facebook, that's just its origin, and there are nice. They're not visualizations, but I guess little things you can kind of click through to show how their privacy changed over time. And I mean, it's basically a sociopathic entity. I mean, really, as an organization, it's not a very, friendly thing. So, but of course, living on social goodness, right? That is the bedrock of their thing. Is that people talk to each other and share things, but they don't want to share things. Twitter is insane, right? It's just a disaster, but it's great, right? Because it's just open. So we'll see what happens. They have this ridiculous IPO recently, so things may change for them. But they're big. The good. So they've profited a lot from the fact that they're purely open. You can have a closed account, but the default is to be open. That's why people go for it. I don't know, Snapchat and whatever's come after that will, may rule the earth. I don't know, but. Twitter has this nice aspect of being embeddable, and all sorts of quotes come from Twitter. Celebrities, sports people. We couldn't talk to them, but they tweeted this. And they put it in the. I mean, you can't help it. The journalists use it, and you look at political stuff, like what people are saying on Twitter. Doesn't really help necessarily, but those things are being talked about and quantified, and of course we have found that. We and many other people have found all sorts of correlations between what happens on Twitter and other sorts of measures. I mean, just mentions of food types correlates with obesity, for example. Obesity, if you look across the states, it's a very nice piece of work. Just a ridiculous thing, right? So we have this thing where we say, if it's a hamburger, it's this many calories. If you say hamburger, we'll turn into a calorie count. If you say hot dog, we'll do this. A mandarin is this, right? And then in a sort of insane way, but then you taken as a whole, it works out. There are lots of things about whether Twitter predicts the stock market or voting and so on. So that's actually much more. I'm not sure if any of that works at all, but it's a good way to start up a Wall Street company, which may not probably last, but it's a good way to get it going. All right. So lots of things. So yeah, there's some coughing here because this is, I mean, this is, I built these things before the NSA became the NSA. All right. Okay, so we had this little example from Brockman of the spinning globe with all of the things, right? So this is built on that data set, and this is some examples of the kind of complexities that you would see if you just look at a map of where bad things have gone, right? So this is a simulation. So it's a disease spreading from Hong Kong. And and the dots are colored for the times that they took and so on, and maybe different areas. And so it's everywhere, right? This is bad. I think New Zealand escaped in this case, so you should. New Zealand is, if you really, you want to get out of the world and live in a great place. New Zealand. Is Madagascar? Oh, Madagascar. No, not good. It's true. I was looking at this before, and I thought maybe New Zealand, maybe Madagascar. I'm like, no, bad. There's some amazingly remote islands down here. There's another set. I can't remember their names off. They're very, very remote. It's not that. No, it's further down. Amazingly remote. Yeah, with humans. Okay, so so this is a bit of a mess. These things, and you're trying to think about where this might have started. And I'm just going to go through this quickly, but the idea is, you throw away the map and then just look at these airline connections. And this is the effective distance and the time for infection here. So this is the distance along the network, not necessarily on the globe, but it's not going to be far off that. But basically, how many so you take the shortest route by planes, and that's your distance. Fair enough. I mean, you could also do it you could turn that into a time thing. And then this Hong Kong is in the middle, and then all of these guys are because it's now it's a network, it's a branching network. So you say you put Hong Kong, and then we'll put spreading out from that, we'll put the cities that are closest to it, and then the cities that are reached as you go, you have to go through them to get to the other ones. And then we'll keep going, right? So these will be cities on the other side of the Earth. And so these are short time, so this is again a simulation, 11 days, 50 days. The days probably don't matter. But you can see it moving out very naturally, very simply through this network. So if you orient yourself properly in the network, which is a big ball, right? So you go and sit on the right place, and then ignore all the cross connections, but just think of the connections going out from you. So now it's just a purely branching kind of structure. Then the whole thing is made much simpler. So it's an idea that's been around for a long time. They did it beautifully. And this is the spreading from Hong Kong here. You can see it's getting into Asia. Europe's got a little bit. Australia's just boop gone. No one lives in the middle, basically. So this is Australia's out. New Zealand, not so good here. Yeah, bad. And then the US is getting it pretty bad now. I guess South America, not so bad. All right, but that you can see if you look at this. If you just looked at this, you might struggle to figure out where this started. Right, the Pacific is gone. Hawaii and Easter Island is in trouble. And then here's the kind of analysis then you can do, right? So you're seeing this thing spreading around. I mean, sometimes these things are definitely kind of a mystery. I mean, in Europe, you have the Black Plague and so on, and it would be called the plague from the most recently known place that it came from. Like blame it on those guys, kind of, right? It's like Turkey or something, right? It's them, But it came probably from some chicken poultry farm thing in China, right? And so who are blamed by those guys, So of course now we have all this data, and as long as countries are good at saying how many people are sick, right? So SARS was a bit of a good example where China didn't really quite say how many people were sick, and so it was a little hard to tell. So you need good reporting structures, systems. So this is orienting it at different places. So that's the idea here, and I'm not sure if you see. I needed to show the high resolution thing here. Okay, so this one is starting at this example I thought was at not Atlanta. Is it Atlanta? I thought this was Atlanta. No, it's not Atlanta. It's yep. Is it Chicago, right? OID is Chicago. No?
It looks like it's Chicago on the map.
It's Chicago, right? Yeah. No, it's a video that's why I'm confused about it. All right, so this is some time into the spread, and you look at who's getting it now, and you make up the branching network for Chicago, and that's how it, how the spread is looking right now. So that gives you a suggestion that it's it could have started there. Whereas if you oriented around, and I can't read these, if you oriented around these places, this is less feasible. So now you can build a statistical test. So again, you can see these kind of visually very much. It probably didn't come from Sydney, Mexico City. This is Atlanta, I think. Is that Peking? Yeah, right. So it's the airport name, right? So Beijing. This circle here. This just
Like, why is it oriented in a circle?
well, so you want to put down here as best you can a representation of the distance from the originating airport. So so this is a real distance here. So you've taken the there's branching in there still, so it's not perfect, but it's a right. So you start at Chicago and think of all of the ways to get to every other big city in the world, right? And then let's say there's a unique path to them.
That makes sense.
And that's going to be a branching, that network is going to have a branching structure, right? So you'll go from, I don't know, say to San Francisco, and then to San Francisco perhaps, and also to Los Angeles, and then that'll take you to Australia and Asia. But that'll fan out there. And then there'll be other places to get to there. Right? So the whole thing is a big ball, but then you click on one of them, and most of the links go away, except for the links that emanate from that one. Yeah, is that okay? So it becomes a branching network. So if it's a branching network and everyone's connected, there are n nodes. How many edges? Well, so here's let me say what I'm trying to say. So you've got the whole thing, there's a ton of edges, right? And you click on Chicago, right? And now the only edges left are these unique paths. So there's only one edge coming to each destination city now. And it's part of the shortest path from Chicago.
So n-1.
That's right, so it's n-1. Because excluding your original one, there are n-1 other guys. Yeah. This is one of those trick questions, like how many tennis matches do you need to reduce a field of 128 to produce a winner out of 128 because it's another branching network, but the other way, right? Well, you need 127 losers. So that's it. So you're sitting there thinking it's 2, and then there's a 4, and 8, and 16, and 30. You can figure it out, right? So this, you have to do the little thing, you're adding 1 and 2 and 4, right? Because there's 1 match and 2 and 4 and 8. So you write out your little thing, you get a little geometric sum, and you're like, it's 2 to the n-1. You're very, because there's a 2 minus 1 on the bottom, you get it all sort of, and then the idiot next to you is like 127. What do you mean? No, you have to figure it out. Sneaky. All right. This is very clever. Yeah. Right? Now, of course, quarantine, people react. This is a simulation, different things. Okay, so just a branch. So branching just means, gosh, I'm a terrible person. It's just, there are no loops. Right? So if this is Chicago, everyone is fleeing Chicago. You could visualize it like that, right? They want to leave. Depends how you feel about Chicago. Is that true? Is that true? Okay, all right, good. I'm just giving you a different way to feel about it, if that works. I know if that upsets you, you can just exclude it. This could be zombies coming out of here. It could be whatever it is. Yeah, so branching network. So there are no edges, no loops. Yeah. No triangles, no loops, no big loops. There could be big loops, right? You could, have this. But in this, the requirement is just to make it a branching one. There could be 2 shortest paths, but because we've got some little bit of, it's on the Earth, there are distances, it should be okay. You should be able to produce a unique, if you say Chicago, it should be a unique thing. Like there shouldn't be 2 ways to get to Sydney that are exactly the same in length. We'll do some, we'll look at this later on too, when you might think about, okay, so you want to redistribute people. That's what this thing is for. This whole airline system is generally, moving people around. So they spend some time in airports. They spend time. So there's a cost of being in an airport. There's a cost of being on a plane. You could think of UPS and FedEx of having, and the post having. There's a cost to the thing being moved around, the object being moved around in a center, and then being, traveling on trucks. Those, depending on how much those two things cost, you'll structure your network very differently, right? So if it's, we'll come to that later on, but you might want a network where it's just everything is in Columbus, Ohio, and then you fly everywhere from that. Or you might want to have one very distributed kind of one. We have lots of centers and little trucks driving all over the place. But it depends on that balance. Which, these places of institutions or corporations have figured out quite a lot. No? Is that okay? Maybe you guys need a shut up button. You politely tweet to me. Stop talking. I'm actually paid to talk. So, all right. So, it's an amazing coincidence. I like talking. Sorry. I repeat things. Repeater. Okay. Okay, so here is a visualizer. This is starting in Mexico City. Is there music? I turned that off, didn't I? Yeah. And everyone is gone. Let's do it again. It's kind of fun. So here's your directed network coming out of, come on. Yay. Wow, so weird. Well, I think, so, I think I just have to get the page again. Is it Adobe? My friend Adobe? No, this is Atlanta, sorry, this is Atlanta. Which, has a few fun things stored in boxes somewhere that if they got out would be bad, right? So this is, this is CDC goes wrong, right? So yeah, New Zealand got it, bought it again, but my hilarious joke up here is Greenland is okay. This is a reference to Princess Bride, The Princess Bride, the movie. You must see it if you have not seen that. You can click on that later. Unemployed in Greenland, Where I Found You. It's Andre the Giant. Andre the Giant. Have you seen this film?
Yeah.
Okay. Okay, good. He's getting into it. He's upset. Anyway. This one is from Greece. Is it from Greece? No, this is Mexico City. Okay. It's just it's the same kind of thing. But you see, yeah, it's all over for, of course, where people live as well, right? But that was bad. Yeah. Yeah. That's my favorite bit of NetSpeak, by the way. So much win. Yeah. It's usually used in a very genuine way. Someone puts up something funny and people are like, so much win. Sorry.
Is this swine flu or SARS?
This is a simulation. This is totally made up. That's why it's so beautiful. No, but the network is real. What's that?
In the original paper, they did SARS and H1N1, so that's why I thought this was from.
Yeah. So let me say something. There are two science papers came out trying to measure the how that thing spread, and we'll get to contagion later on. But one of them you can't tell, but really there's some. This is the infection level. A lot of resurgence, and we talked about this in pox, right? I didn't quite say this, but one of the models that they fit basically was an exponential growth, and they fit one data point, basically. As far as one I recall and understand. The other one was more complicated. It was exactly the kind of thing you want to do, which is, the moves between regions and so on, and right, that it had that kind of more of this. Yeah, it's more complicated. The big problem there is we want to know what the so-called reproduction number is. Like, if you've got it, what's the probability that you infect? What's the expected number of people you infect? Yeah, because we love reducing systems to one number, and it is a disaster. I mean, there are things like the effective temperature for weather. Just say what the temperature is and whether it's raining or not. That's you need to have, and the humidity is that. What's that?
Humans are just really good at that. Just like
reducing things to one thing.
Whatever you can measure is all that matters.
Oh yeah. Yes,
Well,
yes.
Isn't that a famous quote? Pythagoras, man is the measure of all things.
Well, That could be used. That's interesting.
It's an ancient Greek.
The measurer. Yeah.
Yeah, it's a plan.
Yeah. That's interesting. Well, there's the one that I often put up is, to measure is to know,
Yeah.
which is a little strong. And also, there's nothing.
Also
This is Lord Kelvin. There's nothing left in physics. This is 1800s, but just to measure things more accurately. Smacked around a little bit by quantum, and then the chaos thing, disaster. That's really bad. Okay. All right. So there's some fun stuff. Here's just to show you some more examples. Creative networks. So this is a really great paper. This is Science again, 2005, looking at the evolution of networks that produced interesting things. So they had Broadway musicals, and the other three areas they were looking at were academic areas. So I think astrophysics, maybe something like a couple of other fields. And so you can see, so people work together to produce something, and then maybe they keep working together, right? Or maybe they split up and so on. So you can track the way these groups evolve. You can see the same thing with bands, right? You can see it in actually video games. So like the big multiplayer games, again, tons of data. You can see how people literally, of course, band together, and you need to have people with different skills. Corporations do it, right? You need to have teams, right? Sports teams do it. You have specialists and so on. So you can see this sort of thing. It's good data. So they have an actual little mechanism for how these teams kind of. It was a tricky mechanism, but they have a mechanism. So that's good, fun things. All right, okay, good. Just some examples. This is the last piece in network. So we had interaction ones, and then we have these relational ones, which may have impact or may not. This one probably does. Walmart, this is actually from a while ago. They must have more data. One of the things that came out of this was that they figured out they needed to buy more Pop-Tarts when hurricanes were coming, because that's what people tended to buy. They probably bought shovels as well, but they also bought a lot of Pop-Tarts. So, Walmart responded magnificently by simply delivering more Pop-Tarts before a disaster. Okay, so, right. You don't need to know why. You just put the Pop-Tarts in. So as I said, ideas, how they're connected, all sorts of things. Any kind of knowledge databases. We've had clever ways for kind of finding how, for getting us to kind of label things. So Flickr's a good example for finding things that are similar. The web is laden with this, right? It's what made Google work early on. This is terrible on this screen, but I'll just leave it here. This is science, right? So this is this is not something that it's been imposed by anyone to say these sciences are connected to each other. This is it's from PLS1. It's Bolin from a few years ago. You can get a better figure here, but this is basically how people navigate around around journals and so on. So you can see what's really connected. So there's things like physical chemistry, organic chemistry. Child psychology is over here. So you can see this. It's not just a big blob. There's some structure here, right? It's so awful to try and read that. Disappointing. What's the resolution on these things? It's like 800 by 600. That we could fix up. Okay. All right. Well, it does point to this last statement. This is typically the case with a lot of networks, right? They are a bit of a mess. And as I said, structure detection is something we'll come to later on. That's a big deal. There are kind of canned things that people use now. Essentially, it's gotten to that level. So you feed your network in, and it will say, okay, there are 4 big units, which you couldn't see, right? It's this big mess. But you process it and relabel nodes and say, these guys are kind of on the same team, and these ones. And I'll say this again. So actually, next Thursday, I'm away. We'll have Kathy Bliss, who's a graduate student of ours, who's done a lot of good stuff on networks. One of the things she wants to present will be show you something with Gephi, for example, so how to use Gephi a little bit. So if you have laptops, you should bring laptops. But I'll tweet about that. Gephi has sort of become one of the best network visualization tools around, right? There's a few competitors, but it does some good things. So even when they look good, even if you think you've got it, this is my little joke, right? So it's a very graphic analogy. which aids understanding wonderfully while being strictly speaking wrong in every possible way, which is a bit true of some of the flat networks I've showed you. There's some messing around to make it look kind of pretty. Anyway, so we need to work hard to get out the essence of things. All right. Okay, so I'll come back to that because that's part one of the properties here. I'm going to kind of race through this stuff. Wow. Okay. Is it? Is that? Yes, we will talk about that. That clock is correct, like I told it to be. Okay, so we have things like Fourier spectrum where we say, okay, we have we can break a signal down and we can say this is the most important part and then this is the second most important part, or here these things are all orthogonal to each other and we can build a signal out of them, right? Sine waves and cosines, right? So that's a classic example of decomposing something into its vital pieces, right? And there are lots of ways to break things down depending on what they are. Images, wavelets work well for images. So what do you do with networks? How do you break them into pieces? Can you do that? And it turns out to be, there's some natural things you might try mathematically, like counting loops and all sorts of stuff. But when it comes to physical ones that actually do something, that behave, that exist in the real world, these are generally the kind of features that we've come up with in the last 15 years as being important, and they're broad and so on. And I could probably add some more and change things around. But degree distribution is number one, right? That's really the big deal. Okay, what is the tapestry of friendship numbers across this network? Then there's how they're connected together, right? Do all the ones with lots of friends connect to each other and so on? That's this sortativity piece. But first and foremost, this matters, right? So I'll go through these. And then there's, this is of course a giant thing. I mean, how do the networks actually evolve? How do they come about? How does the things happening on top of them operate as well? Anyway, so all right, let's race through some of these. So degree distribution. So we'll write as P sub k. K again is the node degree, number of connections. And so classic random networks, and I'll give you some things on this. I know we did a little bit in POX. This is a Poisson degree distribution. Sorry. And again, average degree. If you want, you could call this Z if that helps make less of a mess here. This is average degree is sitting here, k factorial on the bottom. So this typically has this kind of form. I mean, Poisson degree distributions, right? It's discrete, and I'm not showing that, but it's there's an average degree. The width of it is actually not very big. It's average. The standard deviation grows like average degree as well. Well, variance grows like average degree, I should say. Let me get that. I'm being a little glib there. So it's a narrow network and a narrow distribution. So you don't find nodes with lots of friends. So this is, if you take n nodes and you have m edges and you throw the edges down randomly, make that network, and we'll talk about how to do that. You put it in a box, then you do it again, and you put that one in a box, and you do it again, right? And there are lots of these, and we'll count up how many there are. You throw all of those in. It's not even worrying about weighting them, having weighted edges or anything. This is just pure edges, undirected. Put them in, and then you pull one out. It will have this degree distribution. It will be very, very close. There will be some in there where there's a node that's got, everyone is pointing to that node, and then maybe it's got some other friends, like a really strong star network. There'll be something like that. There'll be ones that have power law size distribution. But there are so few of them, you will never find one rummaging around, right? You will always get these guys. But the universe does not ever produce these, right? Because they are not made, right? This is the thing that lives in mathematicians' heads. So this is a classic degree distribution. There's lots of good stuff, but it doesn't exist. So typically you see these guys. There are different kinds, but typically this is a very common one, so-called scale-free networks. If you haven't taken POX, then we could talk about how to kind of see some of this, inject some of this material. But it's k to the minus gamma. This is a power law size distribution. It means it's like, so we've talked about a lot, things like earthquake distributions, size distributions, wealth is at least heavy-tailed, so-called heavy-tailed. Might not exactly be power law, but these are statistics of surprise, right? You're sampling from them most of the time, depending on the thing, but most of the time you might find small things. Most of the time you have very small tremors that are undetectable, right? Now and then you have one that's much bigger, and very rarely you have one that's huge. And we encode this in language. We talk about the 100-year flood or the 1,000-year flood. Like, we have an idea of it. But generally it's not easy. This is a very hard thing to grasp, right? The 99%, 1% thing, that's exactly trying to encode this in natural language, but it's still, that still doesn't work. But it's not bad. Anyway, so these are the networks have this as well. So, another good example is wealth, right? So if you pick a random person from the US, they're not going to have a lot of money. If you're very, very lucky, you're going to get Bill Gates, right? And it's a ridiculous amount of money, right? But if you're picking out people and then looking at their height, you never get someone who's 10,000 times as tall as the last one, right? You don't get, right? It's a very small, it's gentle, nice little boring distribution, right? Which is good. That's fine. But yeah, some of these other things, and it turns out networks very much are in that category, have these skews. Okay, and the hubs are very interesting, right? So they can block things, they can make things spread, depends, right? I mean, if JFK goes out, the whole airline network on the East Coast gets into trouble really bad. But as we sort of, someone puts out a fantastic disease that no one knows they have in JFK, that's going to be really bad as well, right? So it depends on what's happening on the network. I've said this, so these so-called Addish random networks are a mathematical thing. These scale-free ones they're growing networks, they come from a plausible mechanism, rich gets richer. So there's certainly randomness, tons of randomness in everything we see, but it's just not complete randomness, right? Okay. So fun things to play around with. Spend 50 years playing around with those guys, but okay. Sortativity and homophily are similar businesses. So this is to say that, all right, you've got your degrees and so on, but then there's some more things. So the nodes that are connected to each other are connected to each other for reasons, right? So they match up in some way. So degree, to go back to degree is actually a nice thing to explore. So it's the idea that well-connected nodes may be connected to other well-connected nodes, or conversely, well to poorly connected. And there's some earlier work that has that gets at that. But so it doesn't have to be degree, of course. It could be age. It could be age of not a person necessarily, but a node, like how old an institution is. It could be things that people like, whatever it is. All right. So you talk about a network that's associative if whatever measure that you're talking about for these nodes, they have some little vector of things, and there's a little vector over here, and you correlate them in some way, or check how far apart they are. You talk about being associative if like is connected to like. So that's the birds of a feather story. And disassociative if it's going the other way, right? So these are just very nice things to measure about your network, right? It may be that it's purely random in this. It doesn't have this feature. And we'll look at how to get at this. Right, the first thing you want to say, okay, the degree distribution is what it is, and then I want to see if there's anything on top of that that's not random. Okay, so this is some earlier work. This is Newman. These are Mark Newman at Michigan. You often see this in social networks. We could certainly add to this now, I think, but company directors, co-authors in journal papers, actors in the so-called actor graph, which is a bit ridiculous, but it's the, you take every movie, and if someone was in a movie with someone else, then they're connected. It's the Kevin Bacon game, right? Yeah. So we talked about that. We know about that. So these are often tech ones or biological ones that are disassociative, right? So that they go up and down. So as you move across the landscape of the network, the nodes are somewhat dissimilar, right? Okay. So is that okay? It's just I'm not doing anything quantitative with it, but conceptually, yeah. Okay. So that's the thing that matters. All right, I'll talk about clustering, and then I think we can escape. So this is very important. This is a good measure of socialness. People have looked at this in the past, different stages and different ways, but it really took off in this Small World paper by Watts and Strogatz, 98. So your friends tend to know each other, right? So this little guy here, A, has these friends, and there are some connections between them, right? These two don't know each other, and so on. People are clever, so there might be good reasons for why they don't know each other, right? But anyway, this is a very common part of network. So it's the opposite of not the opposite, but as opposed to a branching network, right? So purely branching networks, your friends don't know each other. And that was a contrived branching network when we take the airlines, because we're just lighting up a particular part of what is actually a network with clustering. But branching networks, your friends don't know each other. So that's a very unsocial kind of network. So a couple of measures, and we'll look at these a little bit. I'll get through these slides. So one is to say, okay, let's look at the neighborhood of A, in this case, or node I, and we'll take every pair of friends, right? So we take B and C, and we check essentially to see if they are connected, right? And that's what this little quantity is here. It's the Ji J2 element of the adjacency matrix. So if that has a 1 in it, you just put a 1. If it has a 0, you put a 0. So this is a funny way of saying just count up how many of the possible friendships in your friend circle exist. Right? And then this is divided by the total number of possible friendships, which is this is a Ki choose 2. So this is a degree choose 2, right? So this guy has 10. This character has 10 friends. Then there are 10 choose 2 possible connections. It's a simple combinatorial thing. It's 10 times 9 divided by 2. The number of triangles story down here. This is a local measure, and then it's averaged over every node. So you're averaging over all the nodes. So if someone has a ton of friends, you just get one little clustering measure for them, and then it's averaged across everyone else. So the nodes with lots of friends tend to be downplayed a little bit here, right? Here they're not. Here they matter a lot, because what we're going to say is let's take every triple. And I'll come to these, but a triple is simply, right? There's a node here, node here, node here. That's it. And then the question is it closed or not? Right? So you count up all of the triples. Even doesn't matter if they're closed or not. You just count up all the triples in the network, and that goes in the bottom. And then you have 3 times the number of triangles. So every triangle closes 3 triples. This one closes this triple, right? This one closes this triple, and this one closes this triple. So this is the number of closed triples divided by the total number of triples, and that gives you the fraction of triples that are closed. So if it's 1, it means that every case where you say, oh, here's a node, it's got 2 friends, they're friends. That's true in every case. If it's 0, then that's never true. And so these numbers don't match up. This is a global measure. You're right, this is a global quantity and a global quantity. This is local, then average globally, different things. But they have some similar fields. Okay, I'm going to tell you these things. I think we're running out of time. All right, so, okay. You have to go. You're excited to leave. All right, people. All right, so on Tuesday, we'll talk more through these things. There'll be more introduction. And Brent, what's that?
Office hours on Tuesday.
Yeah, so I thought maybe we could have office hours straight after.
Class.
Yeah.
Sounds good.
What do you think of that?
But there are also office hours on Wednesday, right?
Yes. Yeah, so we'll have a portion now and then a portion on Wednesday.
So are you around tomorrow?
Now, however, I'm not going to be here Wednesday, Thursday, Friday next week. And so but the assignment is not due next week. It's due the week after. So everyone can chill. It's like talking to my child. I'm just saying. You're trying to affect me with a particular
I will tweet you.
Oh my God. Yeah, sure, please.
I have questions.
I might be. Yeah. Thank you, people. Lots of fun. I know we're just building the engine up, and we're going to do lots of fun things. Okay.